Okay, so good afternoon, everyone. My name is Teng. I'm a PhD student at the University of Manitoba, Canada, working with Professor Pourang Irani. The work is in collaboration with Khalad Hasan, who recently graduated from Manitoba and is now a postdoc at Waterloo, and Keisuke Nakamura, Randy Gomez, both from Honda Research Institute. The title is SoundCraft, enabling spatial interactions on smartwatches using hand-generated acoustics. Smartwatches facilitate quick glances at information when needed. To support this, short and rapid input bursts have become important due to the challenge of the miniature touchscreen. Researchers have investigated many different input methods for smartwatch, such as around-device input. Alternatively, acoustic input using embedded microphones can also enhance smartwatch interactions. These include verbal acoustics or speech input, or non-verbal acoustics such as whooshing or whistling. However, these acoustic inputs are not best suited for spatial input such as scrolling, swiping, or multiple command input. SoundTrack is a recent work that leverages active 3D precision tracking on a microphone array, where a sound emitter is required to be worn on user's finger. And the wideband uses embedded motion sensors to detect acoustic signals that are generated from hand gestures or vibrating devices, and transmit through the varying hand. It is very promising as it requires no extra hardware, but it's not designed for detecting the in-air gestures such from the non-varying hand. So in this work, we present SoundCraft, smartwatch prototype that embedded with a microphone array to capture hand-generated acoustic signals. Hand-generated sound are very rich, so let me first show you a few samples which kind of explain why we are so interested in this kind of signal. So in this early stage exploration, we only focused on different types of acoustics without considering the tempo or rhythm. We collected 56 acoustic signatures in a lab study where we found we can categorize those into the in-air gestures as shown on the slide, on-body acoustic gestures, and on-surface gestures. The different properties of the gestures can be mapped for different applications. For instance, the finger snap is suitable for quick and short activity, while the finger rubbing can be used for continuous input. To demonstrate the use of such acoustic signals, we developed SoundCraft. It was built with a 4 maps microphone, each placed at one corner of a platform that was 1.5 by 1.5 inch in size. The small size of the prototype is good for being adopted for smartwatch, but it also raises challenges for acoustic processing. I will give more details later. Besides microphones, IMU was put in the center for wrist and hand motion detection. I will also explain why we need that later. The device is powered by and communicates with a Linux machine via USB connection. The microphone was set to record the data at a 16 kilohertz sampling rate. I would first show you the capabilities of SoundCraft. SoundCraft is capable to classify the acoustic signatures, such as finger snap or rub. It can also localize angularly in azimuth and elevation dimensions of the acoustics. Besides, the continuous sound can be tracked. Users can also use an external device which plays the sound for tracking purpose. Now I would like to explain briefly how our system works. As such, the microphone array used in SoundCraft were in small size. This brought challenges for us to design a high-resolution localization algorithm, especially for narrowband audible sounds in noisy environment. We considered several algorithms, including time difference of arrival, or TDOA. As shown in the figure, the TDOA locates the target at the intersection of hyperbolae that are generated with forces at each fixed station of a pair. It takes the benefits of not requiring absolute measurement of signal propagating time or emitting time. However, the resolution of TDOA in small-sized sensor array is normally low, especially with the audible sound range, which have longer wavelengths. Thus, we considered a different subspacing approach called the multiple signal classification or music. It is widely used spatial estimation techniques that work on the principle of decomposition of eigenvalues. Generally speaking, music is more accurate in noise spaces. However, typical music uses standard eigenvalue decomposition with the assumption that the target sources have stronger power than the noise sources, and the sources stay stationary during the detection. However, this may not fulfilled in our case. As such, we applied a generalized eigenvalue decomposition method and proposed a real-time update of noise estimation to improve the robustness of our system. This diagram summarized the acoustic processing components used in SoundCraft. The microphones collect the signal every frame. The signals were converted into frequency domain, and the correlation matrix were calculated from the signals. Again, so standard music uses only one correlation matrix that represents current observed frames. In our case, we adopt a generalized eigenvalue decomposition method where we calculate a backward correlation matrix to represent the previous observed signals, and a forward correlation matrix which represents the currently observed frames. The correlation matrix was then used in music to calculate the sound source separation and localizations. To enhance that, for this step, a transfer function was used in this step, which modeled the characteristics of microphone array and its surroundings regarding to the signal propagating. To further enhance the localized sound sources, we used MVDR beamformer working with selected forward correlation matrix that represented the noise information. As the sound source's direction is already known, the acoustics can be enhanced by beamforming in that direction and subtracting the environmental noise. And we assume that for a short time, the environmental noise keeps constant, but for a long time, the environmental noise may change. So we designed a trigger algorithm to notice the system to update the noise information. And we designed a wrist rotation gesture based on the IMU sensor as a trigger to not conflict with the acoustic sensor. And finally, with the separated and enhanced acoustic signals, we used a pre-trained GMM model to classify the gestures. Now we are interested to see how well our system could perform, and we carried out 3 user studies. The first one, we want to see how well the system can localize the acoustics. And the second, we want to see how well it can classify the acoustic signals. And then lastly, we want to see how well the system can perform in situ in a noisy environment. So let's go through each of those. In the first study, we asked the user to snap and type on the azimuth and elevation dimensions with different angular divisions with different angular widths. The study was carried out in a quiet lab environment to help us estimating the best performance of SoundCraft. So it can reach the accuracy. So the average accuracy of the localization is reaching 90% accuracy, and we noticed that when users perform on the azimuth dimensions, it is higher accurate. It is more accurate than performing the gestures in the elevation direction. And also, when the division angle is larger than 22.5 degrees, we can achieve the accuracy more than 90%. So for the second study, we used the same lab setup, but we asked the users to perform 11 acoustic signatures, which are top ranked from the participants. And the average classification accuracy was 90%. We also found that non-impulsive gestures such as finger rub or hand rub have higher accuracy than the impulsive gestures. And the finger pinch, which produced small and less noticeable sounds, provided significantly lower accuracy. In the last study, we choose noisy environment, such as in front of a vending machine or a working 3D printer for the same tasks. 6 top-ranked acoustic signatures from study 2 were used for evaluating the classification accuracy, and users were asked to perform the gestures on the azimuth direction with the 22.5 angular width. So, SoundCraft in the noisy environment achieved an average of 89% localization accuracy. And we found 88% for the classification of the 6 gestures. And we also found a similar trend to those in study 2 that the non-impulsive gestures have higher accuracy than the impulsive gestures. With that, I would like to show you a couple of applications to demonstrate how SoundCraft could be used in our smartwatch interactions. SoundCraft can be used for one-handed list scoring with on-table finger scratching. Users' finger can scratch in different directions to score the list upwards or downwards. It can also be used as a delimiter to support motion sensor-based gestures. It supports 2D pan menu in interactions using the non-varying hand to perform different gestures at different locations. And also, 2 users can play against each other in this ping-pong game by performing gestures at opposite directions. It can perform continuous finger rubbing gestures in the space to support the sketching on smartwatch and also rotating view angles of the drawing. Also, users can also use a tool such as the real scissor to cut the rope in the game. And bi-manual input can also be detected with SoundCraft. They can be used to unlock the laptop in this application. Finally, users can use a mobile phone that plays the sound to explore the aircraft model shown on the smartwatch. So here are the discussions. First, SoundCraft is very similar to other acoustic input where it will be affected by the environmental noise. We demonstrate that SoundCraft can handle some constant environmental noises, but it is prone to be affected by accidental noises, such as people talking or walking or door closing. One possible solution for this is to define a operation zone where users only operate in a certain directional range. And in our work, we only focused on detecting the directions of the sound sources, but we haven't estimated the actual distance. So actual distance may be potentially helping us to creating more exciting applications. And during the study, we found that some gestures are more sensitive to user-specific approaches. For example, some users have difficulty performing the snapping gestures, and people have different habits of performing the same gestures. Lastly, it is somehow necessary to define suitable gesture command mappings to make the SoundCraft useful for real applications on smartwatch. So for conclusion, we present this SoundCraft, a smartwatch prototype that can localize and classify acoustic signals for spatial interactions. With this, I would like to take questions. Thank you. No question? Oh.
Gerard Laputte from Carnegie Mellon University. Great work. You've thought a little bit more about this project more than anybody else in this room, so can you comment a little bit on which applications you think is the most promising? So one I see is probably the one-handed gesture where your other hand is busy. Can you elaborate more a little bit on what other applications you think would suit well to the technique?
Okay, thank you. So in my own mind, I personally prefer the ping pong play game, because that actually demonstrates the potential to allow users to the multiple users to play together just by defining different directions or by different opposite directions.
Thanks.
Thanks.
Any other questions?